So good afternoon, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those who don't know, we are all about bringing conservation, adventure, and science into classrooms around the world. And all November long, we have been celebrating Space Month. So we've been having hangouts with directors of space museums. We've had them with astronauts, NASA engineers. It's been really, really thrilling. And today we are ending it off in the best possible way. I will introduce our speaker in just a minute. But right now, we have 7 classes joining us from across North America, and I want to give them a chance to do a bit of a shout out. So we've got Miss Hawksley's grade 5s in Independence, Missouri. Hi there. 1 grade 5. Hi. Oh, hi. There you go. They're all there. We've got Mr. LaVogue's grade 7/8 in North Palm Beach, Florida. Awesome. We've got Miss Frazier's grade 11/12s in Buena Vista, Virginia. Their mic doesn't work, but they are excited. Awesome. We've got Mr. Clayton's grade 3 through 6s in Victoriaville, California. Hi, guys.
Hello.
Hi. We've got Miss Keating's grade 4s in Thornton, Colorado. All of them, all the classes, with all the enthusiasm. We've got Miss Thomas's group in Shipwreck, New Mexico. Rock, not Shipwreck. Sorry. Welcome, guys. And we've got Mr. Ruffin's grade 5s in Rochester, Minnesota. Last but not least, hi, guys. Awesome. Of course, the reason you guys are all here today is for our speaker. So we are joined live by Yazzie, who is a mechanical engineer at NASA's Jet Propulsion Laboratory, which is one of the coolest, most iconic and storied research facilities in the world. Aaron, there's many ways I could introduce Aaron, but I think the coolest thing is just to say that he actually put his hands and worked on things that landed on Mars on Monday in the NASA InSight mission. So without further ado, I want to leave it to him to take it away and share why he gets to do the very best job in the whole world. So thank you so much for joining us, Aaron, and go right ahead.
All right. So, wow, thank you guys so much for joining today. I'm so happy to see all of you guys, especially the kids from Shiprock. I'm from that area. I'm from the Navajo Nation. So it's really good to see you guys. And all of you guys who are joining live on YouTube, if you happen to be a classroom that I didn't know was joining, or maybe you're part of a Native community, I want to say hi to you guys as well. But everybody, I'm so excited to see you. Like you said, my name is Aaron Yazzie. I'm a mechanical engineer. I've been working at NASA Jet Propulsion Laboratory for the past 10 years. And I work specifically in the area that's called planetary sample acquisition and handling, which sounds really awesome. And it is actually a really cool job because I actually literally sample other planets and comets and moons. And so we figure out how to do that through rovers and through drill bits and through scoops and all kinds of fun stuff. But let me also take a moment to just say Happy Native American Heritage Month. Here in the United States, we celebrate Native American Heritage Month in the month of November, and it's kind of fitting that the last day is the day that I get to do this with you guys. So I'm going to take a moment really quickly to introduce myself to all the Navajo and Indigenous peoples out there. Aaron Yazzie hello, everybody. My name is Aaron. I'm of the Salt clan. That's my first clan that I got from my mother. I'm born for Totochitni, Bitterwater, which is my father's clan. I'm originally from Holbrook, Arizona. That's a border town to the Navajo Nation. And I have a lot of really exciting things to share with you. I'm going to jump into some slides and hopefully flip through them quickly. And at the end, we'll take some questions. So let me switch over real quick. Okay. So yeah, like I said, my job is to basically play in the dirt here on Earth, but also on other planets. And a lot of the missions that I got to support in my career have dealt with Mars. So just to really quick show you, this the red blotch that you see in the middle there is the Navajo Nation. The blue star connected to that is where I'm from, Holbrook, Arizona. I currently live in Pasadena, California, which is over in California, near the ocean there, where JPL is. One of the best things that I love to tell people about why I'm excited at doing the thing that I'm doing is because of where I'm from. You can see the pictures here. Arizona, the painted desert there, looks almost exactly the same as Mars. And it's important to show that when we study Mars, we're studying a terrestrial planet, and Earth is a terrestrial planet, so is Mercury, so is Venus. And so when we study these planets, we're really learning more about ourselves and how our own planet formed, and how it continues to form. One of the first projects I got to work on was the Mars Curiosity rover, the Mars Science Laboratory. Here's a picture of it. It's a selfie that it took on Mars after it took a successful drill. You can see that in the grayish, whitish cuttings there at the bottom. I worked on the team that tested the rover here on Earth. I didn't build anything that was actually on the rover, but I did a lot of testing to figure out sequences and commands that we would send the rover in order to successfully drill and scoop things on Mars. So we have an entire Mars yard here at our lab where we have created a Mars scene, and we put rocks out there and we put slopes out there. We practice driving over them. We practice drilling them. Here's me working with the rover late one night, and you can see how tall it is. It's about 7 feet tall. Specifically, I worked in the sample acquisition part of it. So at the end of the rover has an arm, and at the end of the arm is this turret. And there's a whole wheel of instruments on top at the end of that turret, like cameras and brushes and contact sensors, and a drill. And that drill is what we use to get powder out of rocks and process them and pass them off to science instruments to learn more about what's inside these rocks. And so the turret that is on Mars, we have a replica of one here on Earth, and we put it inside this big vacuum chamber, and we can create a Mars atmosphere in there. We can pump it down to a really cold temperature. We can pump all the air out and put carbon dioxide in there. We can change the humidity, and then we put Mars-like rocks and sand inside, and then we actually practice drilling as if we're on Mars. And so here's the team of people that I worked with on this project. That's me in the top right in my bunny suit, drilling, scooping away. So here's one of the tests that we did where we practiced scooping. And here's a successful scoop that we got here on Earth that our team figured out. And here's the one that we did on Mars. So I feel really happy that I got to directly influence the way that the Mars rover grabs these samples. Here's a drill test that we did here on Earth. And here's one that they actually did on Mars. So this is it deployed, ready to drill, and here it is grabbing that drill. So this was a really fun, awesome project to work on because everybody is so excited about the Mars rover. And it's still up there today, driving around, taking samples, learning a whole bunch about Mars, about if the environment has all the right conditions for life to even existed there. So it's a really exciting mission. I'm really glad that I got to be part of it. And it's still going, just to let you know. This picture that I'm showing here was taken, I believe, like a week ago or 2 weeks ago or so. So keep tabs on that. You can look on the website for the Mars Science Laboratory. They actually put pictures up there every day. The pictures that the rover takes that day, they post them immediately on that website. So it's a really cool place to just flip through a bunch of cool pictures. So the next mission I worked on was InSight, and I don't know if you guys have been able to see in the news this week that the InSight lander successfully landed on Mars on Monday. That was just Monday that this happened, and so this is everybody in the control room high-fiving and celebrating because we landed successfully on Mars with the InSight lander. This is the first image that lander took, which is really exciting. There's a bunch of dust covering that lens because there's a camera cover to protect the camera. And that will get deployed in the next couple weeks. And then we'll have some nice, really clear, beautiful pictures of Mars. So this is what the InSight lander looks like. It's going to land on Mars. It doesn't have wheels, so it'll stay in one spot. And its main purpose is to study the deep interior of Mars. What's going on underneath the surface, underneath the ground. Because like I said, Mars and Earth are both terrestrial planets. They have a core, and they have a mantle and a crust, and they have tectonic activity, and they have volcanoes. They have Marsquakes just like we have earthquakes. So all of these things shape terrestrial planets into what they are. And we really want to know what the differences is and how these types of planets end up developing the way they do. And so there's some main science instruments. The HP cubed is this heat flow probe that can hammer itself down into the ground about 15 feet. And it'll have a whole bunch of temperature sensors all along that little tether there. And we can see the the changing temperature as we go deeper into the surface. And so we know like how much heat is escaping, what's going on underneath the surface. The other one is a seismometer. That's what's underneath the dome that you see there. The seismometer is this really sensitive instrument that has these sensitive little feet, and it feels the ground, and it can feel any type of movement or tremor or Marsquake. It can feel a meteorite hit the other side of the planet. It's very sensitive, but it tells us every type of activity that's going on below the surface and all around the surface, to inform us how the landscape shaped into what it is. The rest of the instruments that you see arrows being pointed to are what they call auxiliary payload. And that means that it's just the eyes and ears of the spacecraft. We want to know what's going on around the lander so that if we have a lot of wind one day, we know that it's not something funny happening underneath the surface, it's actually just wind. Or maybe the pressure has changed, or maybe the axis of the planet is rotating on a different axis according to what time of year it is. Anyways, I worked on one of those pieces. It's called the pressure inlet, and that's what it looks like. And so this is a piece that I actually got to, I was given the responsibility of designing and delivering this part, and mounting it to the lander and making sure that it passed all the requirements and that it was ready to fly and do its job on Mars. So it was a really awesome role for me to have. And it's the first time I got to send anything into space, and the first time I ever landed anything on Mars. So it's really exciting. So here's just some images that we use. This is some images of the development of the hardware. Here's a test that we did. You can see on the right side that that's something that I modeled up in 3D in a CAD program. That's what we use a lot to engineer things, just 3D modeling. And then on the left is the actual part made physically. So it's really cool to see how you can design something on a computer and then how it actually translates into a physical part and looks the way you want it to look and function the way you want it to function. Here are more pictures. We did 3D printing of this inlet so that we could do some wind tests and water tests to see how air would flow around the disc on this piece. Just a really quick recap of what this part does. It's a pressure inlet, and so it's hooked up to a pressure sensor. And what we want with this pressure sensor is to get a really accurate reading of the pressure in the atmosphere on Mars, but we don't want wind to tamper with our readings. And so we use this inlet, which has a series of holes inside those discs to allow air to enter inside of it, but doesn't let wind enter inside of it. So we only get still air, we get static air. So that's what the pressure inlet does. And so here's the final product, it being all built up in the lab, and then there's a picture of me actually mounting it to the flight deck of the lander. So here's a picture of it when it was being built. This is the actual flight lander. We also have a replica lander here on our lab, and I got to help with a lot of different type of testing. This is deployment testing. So like I said, the lander will actually place instruments on the ground. And so this is one of those tests where we are practicing putting the instruments safely on the surface of Mars. And the big news is that this successfully landed on Monday. And so this is one of the first pictures that it took with its camera that's mounted on the arm. In the next couple of weeks, it's going to deploy the arm, and it's going to start moving joints and making sure that everything's working right. And it'll probably take a whole bunch of pictures of the area that are around it and the top deck. And then it'll start to deploy instruments and start doing science in the next 30 days or so. So keep tabs on this. You can look up the Insight Mars NASA website and see, just like Curiosity, you can see the pictures that it takes every day. As soon as they post it, as soon as we get the pictures back from the spacecraft, it goes right up on that website. So you can see at the same time that scientists around the world see it. And currently, this brings us to the present. So right now, for the past 2 or 3 years, I've been working on the next Mars rover. It's called Mars 2020. So here's a conceptual model of what it looks like. And you'll notice that it looks almost exactly like the MSL rover. And that's on purpose. We know that type of rover works really well, and we wanted to use the same design. We changed a few things. One of the biggest changes on it is at the end of the arm is a new drill. It's actually a coring drill. So we won't drill into a rock and turn it into powder. We'll core a rock and preserve a nice core of the rock. And the whole purpose of this is that if we can get a core of rock that has been preserved in its structure and bring it back to Earth, we can learn so much about the history of Mars and its geography, and if there's actually life preserved in the inside the signatures that we can see inside rocks. So we'll actually determine once and for all if there was life on Mars or if there is some type of life going on there right now. And so this rover is the first of possibly 3 missions where we're going to try to bring samples back from Mars for the first time in history. So the rover, Mars 2020, will go up, it'll drill a bunch of rocks, and it'll save these cores of rock, and it'll put them in a cache. It'll store them somewhere. We'll send another mission up to fetch all those samples and launch them into orbit around Mars, and then we'll send a third mission to capture those orbiting samples and bring them back to Earth. So the really cool thing about this is that I'm currently working on the very first part of this mission to capture samples. And you people your age, like you as a student in elementary or junior high school, you could get through college and start to work at JPL and work on the mission that will bring back these samples. So that's really cool to think about. Like this is in your lifetime. This is something that you could do when you grow up. And so I'm actually in charge of the drill bits. So the end of the arm has the coring mechanism, which is shown there, and we'll drill with the drill bits. And you can see a little sample tube there, which goes inside every drill bit, and it preserves the rock that we drill. And so here's just a little development slide of the work that I do for these drill bits. This is a coring bit. I usually start with paper and pencil to draw out some ideas and concepts, and then I make a 3D model of it in a computer. I turn that 3D model into an engineering drawing, and then I can actually build parts. And all along, you can see in the background are just calculations and analysis that make all that really fun. We're actually going to send 3 different types of drill bits with this rover. So we have the coring bit in the top left. We have an abrading bit, which you see in the top right. That's just going to drill a shallow depth hole, about 2 inches in diameter. And then we use a little puff of gas to blow the dust out of there. And then we have a nice, beautiful flat surface to take our instruments and cameras down to and take pictures of signature of the rock underneath the surface. The bottom picture is the regolith bit, which is basically a bit that can gather loose soil and sand. Here's some development hardware that has been going on recently. This is actually the coring mechanism, so the whole mechanism that actually allows us to drill into rocks. Here are some drill bit parts that I've been putting together. All of these parts have the teeth that we're going to use to drill into rocks. They're getting brazed into the actual part. So it's just a really cool picture of all of them lined up. They're about to go into a furnace. And these are development coring bits that we made. So we're using these for tests right now, and we're using all that information to help inform us for when we make our final flight ones. But this is what they're going to look like when we finish them. You can see that they're just beautiful colors all around. Like the end of the actual drill bit body is going to be covered in titanium nitride, which is what makes it gold, and that really helps us with planetary protection, which is a big issue. We don't want to bring things from Earth to Mars, and we don't want to bring bad things from Mars to Earth. And so this special coating helps the bad spores and molecules to not attach to the surface of the drill bit. Here's us doing some drill tests and a giant test bed. So like the pictures I showed you before of the giant vacuum chamber that looked about the size of a walk-in closet, we are now using a giant vacuum chamber that is 10 feet high, and you can actually walk inside. So it's a giant testing chamber, and it can do so many cool things. And so I'm up there usually helping to oversee or help run tests every day. It's a really cool job to do. And so, yeah, that brings us full circle. That you saw this image before. I just want to drive home that Earth and Mars are not very different. We have the things that created the geography and the landscape and the rocks that we have here on Earth are the same things that shaped Mars. So it's a really fun thing to study Mars and see how a terrestrial planet can develop differently just based off of where it is in the solar system or what's going on beneath the surface. And for me, especially being Navajo from the Navajo Nation, the area around our homeland is so similar to Mars. And the picture here you see is on the left is Canyon de Chelly, back home in Arizona. And you can see all the layers in the canyon. They actually say that this canyon was developed a long time ago. It used to be a giant sand dune, and then sandstone was created and carved out this beautiful canyon. And so there's just so many stories that we can tell from the canyon, just looking at the layers, understanding how something like this can be formed over millions and millions of years. It's the same thing that we're doing with Mars when we study the layers of rock, when we study how landmarks have formed. We know that the land has a story and we want to learn it. Here's a picture of Monument Valley up in the Navajo Nation, and you can see that the ground is so red, just like pictures of Mars that we get back. Here's a picture of my grandma scooping the ground, just like I was scooping on Mars with the Mars Science Laboratory. I like to look at this every day and just remind myself how far we have come as humanity, and for me and my family. We as humans have advanced so much to being able to send things to another planet and remotely scoop and study them. It's incredible. And one last image, this is the same landscape, but you can see on the left is a picture of a hogan, which is the traditional Navajo house, and then on the right, the Mars Science Laboratory. And so if you closed your eyes and looked at both of these pictures, you wouldn't be able to tell if you were here on Earth or if you were on Mars. And so I just want to keep driving that home, that when we study Mars, we study our homeland. That's it. Let's jump into some questions.
Aaron, thank you so much for that. You're an inspiration, man, and I'm sure I'm not alone, and my face hurts so much from smiling at that entire story, so thank you. We're going to start actually with a group that's watching on YouTube Live. I know they're a class that's special to you. So Mrs. Salomko's class, Pechanga School, grade 4th and 5th graders, I wanted to ask, how did you know that the InSight landed safely? Oh, good question.
So there's an entire entry, descent, and landing team and sequence. So there's a whole bunch of people that have developed this plan that allowed it to land successfully. They knew that every single minute, every single second, they knew what the lander was supposed to be doing, and they design little things to help give them hints that everything's working properly. So if it separated from the heat shield successfully, it would send us a little beep signal. If the parachute deployed properly, then it would give us another little beep signal. And so we had to rely on these little beeps and signals from the lander to understand that everything's happening as it should. I don't know if you, so one of the things that's most challenging about landing things on Mars is that it actually takes some time for signals to travel between the two planets. So it could take between 6 and 7 minutes, depending on the type of frequency you're sending and the distance that Mars and Earth are from each other. And so when we were actually seeing it live, they were sort of guessing. They're like, well, it should have landed by now, and it should have done this by now, but we don't know because we haven't gotten the signal yet. It's still traveling on its way to us, and it'll get to us a delayed 6 minutes later. And so that's always the challenging part. But they did an amazing job of planning out that entire sequence, and everything went exactly as they planned it. So when it landed, they got the beat that it successfully landed, and then they got images to show that it was successfully landed and not upside down or anything like that. So.
Excellent, great answer. And that actually reminds me, so classes, you can watch on YouTube the entire sequence of mission control, watching the InSight get closer and closer and going through those steps, and I really encourage you to do that. Also, as we took a class from a group online, for anyone who's watching on YouTube Live, you can pass along questions, and I'll pass them along to Aaron. Let's start with Miss Thomas's group, another group that's special to you. So yes, in Shiprock, if you guys want to take us away with a question, go for it.
Okay. Sorry, guys. We have our first question. My name is Luan, and hi, Aaron.
Hi.
My question was, what kind of scholarship does Stanford give you?
That's a good question. So for everybody that doesn't know already, I grew up in Holbrook. I graduated from high school in Arizona, and then I went to Stanford for college. And so I studied mechanical engineering there, and I graduated with a bachelor's degree in 2008. And yeah, I was very lucky to have a lot of help financially from a lot of different places. So the Navajo Nation gave me a scholarship called the Chief Manulito Scholarship. I got a big scholarship from Stanford. Some of it was because my family didn't financially could use the money, and some of it was because of merit, because of how well I did in school. But they gave me a very nice scholarship. Outside of that, I applied for a whole bunch of different other types of scholarships too, like Walmart and Tylenol and whatever I could find, I applied to. So yeah, I was very lucky to have all that.
Excellent. Well, you've repaid them in kind with all that you do, so I'm sure they're all very proud. All right, let's go to Miss Hawksley's group. If you guys have a question, go right ahead. Oh, you were muted. Yep, you're good to go.
How many tests do you have to do before the spacecraft is ready?
Ooh, that's a good question. The short answer is a lot. We have to do a lot of testing, and it's kind of all along, sprinkled all throughout the life of a project. So when right now, I'm designing drill bits, and so we wanted to make sure that just the first concept that we came up with, the first idea we had was even a legitimate idea. Like we wanted to weed out all the crazy ideas, and so we would build prototypes and we would test those out on a small scale, and then we would use that to inform our later designs. After I actually deliver the bits that I intend to fly to Mars, then we're going to do another set of testing that qualifies them, that makes sure that they're going to do all the things that we designed them to do. And so that'll probably be a whole suite of tests that will take maybe like a full year to do. But it'll be a lot of rock drilling tests, a lot of sample regolith soil acquisition tests, that kind of thing.
Excellent. All right, let's head to Mr. Laveau's class.
If you could go anywhere in space to Joe, where would you go and why?
Ooh, good question. Man, I mean, I love Mars for all the reasons I said. Like, it reminds me of my home. It's very similar to Earth. I want to see what it looks like and feels like to be there. I'm also really interested in Europa. Europa is a very exciting. It's a moon, actually, but they have a giant ocean there, and it's amazing to think about there being a bunch of water somewhere else, just like there's oceans here, and what's inside that water, and is there life under there? What does the surface look like underneath the water? And so we actually have some missions that are in the work now to send things to study Europa and see. There's a big icy layer on top, so we're going to see what's going on the top layer, what's going on underneath the ice. So that's going to be really exciting.
Very cool. All right. So Miss Fraser's class, I know your mic doesn't work, but if you guys want to type in a question in that chat bar, please do. While you're doing that, we'll go to Mr. Clayton's class. If you guys have a question, go for it.
How long did it take to build the robot?
Say it again, louder.
How long did it take to build the robot?
Ooh, that's a good question. I think every mission is a little bit different. the Curiosity rover, it was the first time we built a rover of that size, so it took a lot longer. It probably took like, I don't know, 15 to 20 years from the very first concept all the way until we actually flew it. The InSight lander, we actually used a lot of ideas from a previous mission. So there's another lander that we sent to Mars called Phoenix, and that landed on the polar ice cap of Mars. And that was all successful. It worked great. And so they decided, oh, since that lander worked so well, let's use a lot of the same ideas for the InSight lander. And so since a lot of that design was already figured out, we didn't have to do as much development or testing. And so it happened a lot faster. So that one probably within, I don't know, 8 to 10 years, we were able to design InSight.
Awesome. Well, actually, that leads us to a really similar question from Miss Stafford's grade 5, or Miss, Stafford, Connecticut, Miss Erickson's group, grade 5 class, wanted to ask, how long can these things last on Mars?
Oh, okay, yeah. So usually what happens is that NASA, whoever designs the mission, will tell us how long we should expect to work on Mars. And usually that ends up being about 1 Martian year. 1 Mars year is about 2 Earth years. So we as engineers, we design for it to be able to work for 2 years, and then we add some extra margin on top of it, saying like we don't want it to completely just die after 2 years. We want to be safe. We want to be confident that it's going to fill up that entire time. So usually we'll design it to last for 4 years or maybe even 8 years. In the instant, there's actually a really cool example of that is that the Mars exploration rovers, these are the rovers that went up just before the Curiosity rover. They're smaller, and they're usually, some people call them the twin rovers. Those were designed, the mission said, we only expect them to work for 90 days. Like if the rovers are up there and they survive and they do what they're supposed to do in 90 days, we'll be happy. It'll be a success. And then they just continued to work, and they continued to work, and they continued to work. And they, I believe one is still, one of them has shut down. The other one's still going, kind of stuck somewhere, but it's been 12, 13 years since those have been up there. And so it lasted a whole lot longer than we planned for it to last. But yeah, it's just good engineering that helps that happen. But to answer your question, usually they're planned to work for 1 Martian year, which is 2 Earth years.
Very cool. All right, I want to remind Miss Fraser's class again, you guys can type in a question, so please do, little blue square top of your screen. But let's go to Miss Keating's group with all their many, many, many kids.
How long did it take for the rover to land on Mars?
Ooh, good question. So the Curiosity rover, like I said, it's just a giant robot. It's the size of a car. So it's the heaviest thing we've ever sent there, the largest thing we've ever sent there. And so we had to design parachutes that are bigger than we've ever had to use. And we had to come up with a landing sequence that was completely different from what we'd used before. And so as complicated and as new and as large as everything had to be, everything took about 7 minutes, which is crazy. So from the time that the capsule reached the very top of Mars's atmosphere until the time that the wheels touched the ground, all of that only took about 7 minutes. And so it's really incredible the work that team did to make sure that everything went perfectly right within that time.
Excellent. Ms. Forsyth's class wants to pass along the question, which is, how much did InSight cost, the whole project, if you have a rough idea?
Man, I don't even know how much it would have cost. But like I said, since we borrowed a lot of ideas from previous missions, it was a relatively cheap project compared to other things that where it's completely new. And so usually when people talk about NASA missions, they hear things in the millions and billions of dollars, which sounds like a lot of money, and it is, but we are funded by NASA, which is a government organization. And so we get our money from the money that people pay in taxes. And if you consider the amount of money gathered by taxes in the US, NASA only gets a small fraction of 1 penny of everybody's taxes, which means that it's very little money that people are using to support this incredible agency that does so much science and inspires people to go into STEM fields and discovers all these new technologies. So it sounds like a lot of money, but I like to say that it's actually really not. It costs pennies to you guys.
It's 4/10 of the budget goes to NASA, and at its peak, it was a little over 3. So at the very most NASA ever had, it was 3 cents on the dollar for all that work, all the astronauts, all the engineers, everything. So it's a great price to pay for all you guys too. All right, let's go to Mr. Ruffin's class. If you guys have a question.
Right there, you can stay right there.
Why did you choose this job?
Say that again. Why did I choose what?
Why did you choose this job?
Oh, good question, man. So I love being a mechanical engineer. So one, I like engineering. Math and science. I was strong in math and science. I really like to build things and be creative. There's so many different types of engineering you can go into. There's electrical, thermal. There's chemical, mechanical, civil. All these different areas you can go into, and I really like mechanical because it allows me to build things, to design things, to be creative. I also really like art, so I like to draw things, and I felt like mechanical engineers just kind of get to invent really cool things. And so JPL, the Jet Propulsion Laboratory, they deal only in unmanned space exploration, so all robotic missions. So we send all these really cool robots that require a bunch of mechanical engineers to come up with crazy ideas and just basically continue to have fun. I don't know if when I was your age, I like to do a lot of just projects on my own, building things, joining competitions at school, all that kind of stuff. So it kind of feels like I get to do that fun kind of stuff for my job, which is really cool. And so that's why JPL is a really great place for mechanical engineers, and that's why I really wanted to work there.
Outstanding. So Ms. Frazier's group, I love this, that they wrote it on a board backwards. So what degrees do you need to get into your field, Aaron?
Good question. There are so many different types of engineers and scientists here. So if you go into any of those technical fields, you can work here. I did mechanical engineering, and I actually there's all varying different levels of degrees you can get. So you can get a bachelor's degree, you can continue on and get a master's degree, and some people continue on to get a doctorate or a PhD. And we have about equal amounts of all of those at JPL. So I graduated with a bachelor's degree and started working right away. So yeah, that's I would say any STEM field with a bachelor's, master's, or PhD.
Excellent. Another group online, Mr. Galato's class, wants to ask, do rovers only go to Mars if we sent them anywhere else?
We have sent a lot to Mars. I think the only other thing that we've sent up maybe is to the moon. There's rovers up there. There's things like places like Venus is a very interesting place. We would love to send something there, but Venus is so hot and the atmosphere is so harsh that whatever we send there usually ends up we can only plan for it to last for a couple of hours, and it's really hard to have some kind of turning mechanism work on such a harsh condition. If we send something to Venus in the future, it'll most likely just be a lander that stays in one spot. But they're coming with a bunch of cool, like I said, the Europa mission is going to have a lander. They might send a rover over there, but if it's liquidy like they think it is, maybe they'll come up with robots that can swim in water and can climb on ice and all this kind of stuff. They actually have rovers in development that can climb up rocks. So there's a lot of different things besides rovers that we can send out there.
Very cool. We've actually done a lot of hangouts with scientists working on Europa Clipper and landers and robots that climb on rocks. So if you want to see some of our past hangouts, we have covered the gamut. All right, let's do another round. We are ripping through these. So let's go to Ms. Thomas. Scientists working on Europa Clipper and landers and robots that climb on rocks. So if you want to see some of our past hangouts, we have covered the little delay there. So Ms. Thomas's group, when you guys hear this, come on up.
And my question is, how long was the lander in space?
The lander, you said? How long was the lander in space?
How long was the lander in space?
Okay. So if you're talking about the InSight lander, that's the one that just landed on Monday. So it's only been there for a week. It's been there for just a short amount of time, but it's planned to work for 2 Earth years. And then it'll just continue working until we can't operate it anymore. So it'll be there for forever, basically. The rovers that we sent up before, the Curiosity rover landed in 2012, and it's still driving around and working. So they're lasting for a long time.
Just in case this was the nuance in the question that they might have meant, how long was it actually in space, like traveling from the Earth to Mars?
Ah, got you. Sorry, I didn't hear that part. That's a great question too. So when we launch things between Earth and Mars, we usually try to plan it out so that we launch when the 2 planets are very close to each other. So Earth takes a certain path around the sun, and that takes 1 Earth year. And then Mars will take a different path around the sun, and that takes about 2 Earth years. So it has this longer travel around the sun, and every 2 years they get really close to each other, and then they start to distance apart. So when they're really close to each other, that's when we try to launch between the 2 of them. And so when they're the closest together with something about that heavy, but with that mass, it takes about 6 to 9 months to get there. I believe the Curiosity rover took 9 months to fly, and InSight took about 8 months to fly.
Wow, very cool. All right, let's go to Ms. Hawksley's group. You guys have a second question? Come on up.
My name is Justin Harris. I have a question. What checks and balances do you use to make sure that you don't make any mistakes?
Oh, that's such a good question. Because that's a big part of what I do is figuring out those checks and balances that we need to do, because we don't expect to get everything right the first time. It's a really hard thing to come up with a concept and a solution for something that has never been thought of before. And so we'll start with small ideas, and we'll do little checkouts. We'll build prototypes, and we'll do little tests to see if that idea works. If it fails, then cool, that's fine. It's fine to fail along the way. But we learned a lot from it, and we use that to inform the next phase of the design. Another thing that we do is that we have a lot of really smart engineers that have been working at JPL for a long time, and we actually have points in our project where we present our concept, our design to a room full of these really smart engineers, and they'll give us really good feedback. Sometimes it's scary and intimidating to stand in front of them and present this idea, because I feel like, what do I know? I'm so young and inexperienced. But they have such a really good environment where they want you to do good, and they want you to be a good engineer. And so it's a really cool program or method of giving good feedback for this type of thing.
Outstanding. So glad we got that question. All right, let's head to Mr. LeVogue's class for second one.
What do you hope to find on Mars?
Ooh, good question. So just when we sent up the Curiosity rover, the main thing that we were looking for with that was to see if we could find in the rocks or the sand that Mars had all the components that you need for life to have existed on Mars. So that means that was there water there? Yes, we discovered that there's water there, or there was water there. And are there the type of components, like carbon is a big building block of life, and if that exists inside the rocks, then maybe that means that life existed there. And so basically, Curiosity wasn't actually looking for life itself. It was hard to do that, but what they could do was see if all the atmospheric components were right for life to even be a possibility. The next Mars rover that we're sending up there, where we bring back a rock sample, that's where we'll actually be able to determine once and for all if there was life there. And so a lot of this isn't so much because we want to find aliens. That'll be a big discovery, of course, but like we really want to know like how things evolve in our solar system. So understanding how terrestrial planets form, and then understanding how life might form from terrestrial planets. That'll just help us as humans understand where we came from and where we're going, and if it's possible out somewhere, either in our solar system or in another solar system, for life to be there. And it'd be great to understand that.
Outstanding, Aaron. So we had Miss Fraser's class again with a nice long backwards question. If you guys could write that straight, that would be great. Oh, we'll try. Let's try and do it backwards, Aaron, the two of us. Okay. Why doesn't NASA send plants, water, and topsoil to Mars and have the rover take care of oh dear.
I think I get the gist of the question. You're asking. It sounds like you're asking if we're looking for life and we're looking for all these conditions to support life and plant life, including plant life. Why can't we just bring it there and just take care of it and grow it and see if it survives that way? That's a really great question and a really good concept and it's something that people think about. They call it terraforming. That's sort of like creating all the conditions you need for stuff from Earth to thrive there. And so the things that make it a little bit difficult is that Mars gets so cold, much colder than Earth does. It also gets really hot too. It's a weird thing where it's got a very thin atmosphere. And so the sun affects it a lot easier than the sun affects things here on Earth. So when the sun goes away, it gets really cold. And when the sun comes back, it starts to get really hot. Also, the atmosphere doesn't have the same type of things that we have here. They're mostly carbon dioxide. And we know that plants here like oxygen. And so it just won't have the same type of atmosphere that it needs. And also there's no water currently on Mars. There might be stuff below the surface. There might be water frozen at the polar ice caps. But there's no flowing water right now, and plants need water. And so we would either need to bring a bunch of water with us, or we would need to figure out a way to create water on that planet, which would be a really incredible thing to figure out, to discover and create, but it would take some time.
Outstanding. Okay, so we've got time for a few more questions from some classes. I know we're getting to the end of people's days for classes on the East Coast, so we'll whip through them as quick as we can. So Mr. Clayton's group, if you guys have a question.
It's called How long did what kind of pieces do you use for the robot?
What kind of pieces do you need to build the robot?
So what kind of pieces do I need, or parts or hardware do I need? So the robots that we send up are mostly made out of a lot of metal, but also some new types of materials. Like we have we call them composite materials, and that just means it's like either some kind of plastic or some kind of fiber or rubber or something that's not metallic. The hardest part about it is that I was describing with Mars, it goes through such different temperature swings. We have to make sure that the materials will survive all that stuff. So we actually have a really good materials testing group here that will help us determine if the materials we're using are good and they're going to survive.
Excellent. All right, let's go to Miss Keating's group. You guys have a second question? Yeah.
What's your next mission?
That's a good question. So after I'm going to be finished building these drill bits for Mars 2020, probably next calendar year, and then the mission's going to actually launch in the year 2020. I'll probably work on it as long as I can. I would love to help develop sequences and commands for the rover to be able to drill successfully with the bits that I built. And I would also love to join the next Mars sample return mission. So like I said, this is the first step in being able to bring these samples back from Mars. So I'd love to just stay with it and develop the fetch rover that will go out there and grab these samples and launch them back to Earth.
You're already designing the thing that's going to grab the sample, and you could design the thing that picks it up, and then your fleet would just skyrocket. Okay. Cool. Let's take one more from Mr. Ruffin's class before we do one more on YouTube Live. So Mr. Ruffin's class, go right ahead.
What happened to the water on Mars?
I think that it's the way that a terrestrial planet might develop, like the way, the distance from the sun and the atmosphere that it has. It probably caused the water to be able to evaporate faster and leave the planet faster. Yeah, the conditions here on Earth are kind of perfect for water because not only is it there's a lot of it, but also our atmosphere preserves water in the air. So that's what humidity is, and that's how rain forms. So we actually kind of recycle our water over and over again, which is why there's so much water all the time. And Mars doesn't quite have that.
All right. So you began this hangout with such a beautiful description of your culture and history and the land you grew up. And so I want to end with a question again from Arlene Lomko's class, which is, what values in your culture have helped you in your profession?
Oh, that is such a good question. This is probably true for a lot of cultures out there, but especially for mine, is that we really respect our elders, and we always try to be helpful, not just we try to be helpful to others, and a lot of it is being helpful to the community. And so I always like to describe it like we are the younger people, and we're getting older, and we see that our parents are the ones sort of doing the jobs that are running the world. They're the ones that are the president, and they're the ones that are doing NASA jobs, and they're the ones leading all of these types of things. And pretty soon we're going to be the ones doing that. And so we kind of have to step up and be useful, and we have to understand that that's going to be our job someday. And so it's never too early to start thinking about what you want to do and how you want to get there, and find out how you can be useful.
Outstanding. Before we wrap up, is there any, I mean, that was a great last message in and of itself, but I don't know if there's anything else you wanted to share about inspiring kids or your mission or anything else.
Yeah, so I just want to say I hope you guys are inspired by the mission that I shared, and the things that we're doing to explore other planets and to advance the science and knowledge that we have of our solar system. If that's something that you're interested in and that's something that you want to do, then just keep with it and do that, and continue to build things on your own, and to join projects at school that allow you to flex those muscles and be creative. I feel like I'm the same kind of person I was in elementary school as I am today, just curious and having fun building things. So if you want to do it, you can do it too.
Outstanding, Aaron. Well, what we do at the end of every hangout is I'm going to demute every class's microphone. So boys and girls, if you guys could get ready and joining me and saying a huge thank you to Aaron for joining us today. You are all set, so please go right ahead.
Oh my, thank you guys so much. Thank you.
Awesome. To all our classes, thanks for joining us for Space Month. Thanks for wrapping it up with us with this amazing hangout by Aaron, and we look forward to having you back soon. Aaron, that was so cool, man. You're an inspiration, and congrats on what must be a really exciting week for you and yours. Thanks for joining us today.
Yes, no problem.